Hello everyone. Welcome to the SWAM NPTEL course on Mathematical Geophysics. Today we continue Module 5 Diffusive Processes in Geophysics. This is lecture number 4 Solution of the Magnetic Diffusion Equation. In this lecture, the following concepts are covered. The solution of the magnetic diffusion equation. We have seen the derivation of the magnetic diffusion equation in the previous lecture. In this lecture, we will cover the following 5 components: diffusivity limit, method of separation of variables, diffusion in 1 and 2 dimensions, and further we will look into various applications in geophysical studies. So let us begin. The diffusivity limit. We have seen the derivation of the magnetic induction equation from Maxwell's laws. The electromagnetic induction equation is given as equation number 1. This equation states the evolution of the magnetic field B vector with respect to time. Now, on the right hand side there are two terms. One is curl of U cross B plus eta Laplacian B. The curl of U cross B is dependent on the velocity u and the magnetic field vector B, and this is known as the induction term. While the second term is eta Laplacian B. Eta is magnetic diffusivity and B is the magnetic vector. Now, in general, these two processes occur simultaneously, but in the diffusivity limit, when eta tends to infinity, the second term dominates. Also, if the velocity is very low, that means slowly moving dynamics of the fluid flow, then also the first term becomes very less. Thus, either the velocity becomes small or the diffusivity becomes large. We have the diffusion process dominating over the induction process. This leads to the non-advective induction equation as equation number 2. This is del B by del T equals eta Laplacian B. We can see that this is a partial differential equation. Here B is a function of x, y, z spatial coordinates in Cartesian system and t is the time. Thus, in Cartesian system, the Laplacian is given by this expression. Now, let's say B vector is given by the modulus or the magnitude B and the direction is x vector. Thus, the one-dimensional non-advective induction equation is now simplified from 2 to 3, given by del B by del T equals eta del square B by del x square. Here, B is only a function of x and t and hence the one-dimensionality. Now, we are going to look into the processes and the methods which can be utilized from this equation. First, we will solve this equation and see what are the consequences of the solution and the characteristics of these solutions. This diffusion of the magnetic field is very useful concept in relation to geophysical studies, which we will also consider later. First, let us look at the method of separation of variables which we will be utilizing for the solution of this equation. The function b, which is dependent on x and t, is separated into two functions. The product of x, which is function of x only, and of the product of x and t. Here x depends on the spatial coordinate x, and capital T is a function which depends upon the time t. Now, substitution of this equation into equation number 3 gives us x into dt by dt equals eta t del squared x by del x square. This is the variable separated form. Note that the variable separation form is just an assumption. In general, it may be that B is more general than the variable separated form. But this type of analysis gives us an easy method of solution which is also insightful. Now we have to divide both sides of equation 5 by the product x into t. This gives 1 by t del t by del t equals eta by x del square x by del x square. Now, look at this form. The left hand side is only a function of time, whereas the right hand side is only a function of space. Now, since they are equal, it cannot be equal to any dependency on either time or x. Thus, these two parts, left hand side and right hand sides, are equal to constant. Thus, we can write both left hand side equals to k, equation 7, right hand side equals to k, which is equation number 8. We can solve this 7 and 8 equations separately to get the functions x and t separately. And then we can put it back into equation 4 to get the solution for the magnetic induction equation in one dimension. Now, let us look into the solution. First, we have the time part. So from equation 7, we can proceed as del t by del t equals tk. So here t as a function of t will be replaced by only capital T for notational convenience. Now we have by integrating both sides, we have integral of dt by t equals k dt. This gives the natural logarithm of t equals kt plus c. This can be further derived into t equals e to the power kt plus c. Now, e to the power c can be written as a constant capital P. So, we have that function capital T equals a constant P multiplied by e to the power kt. Now, k is known as the time constant since it is a coefficient of t under the exponent. Now, we can have two possibilities. One, k is positive, the other k is negative. And the time solution would be t equals p e to the power plus kt and t equals to e to the power minus some kappa t, where kappa is equals to minus k. Now we can have two cases. Depending upon the sign of k, the solutions would be for k positive t equals to p e to the power kt. Here k is positive. For k negative, we can use minus kappa, where kappa is positive. And we can write e to the power minus kappa t. So here kappa is positive. Thus, we can have different behavior for different sign of k for the time solution. Now we look into the space part. Here we will determine the function capital X. So from equation 8, for notational convenience we will be using capital X only in place of capital X as a function of X. We derive d square x by dx square equals k by eta into capital X. Now let us suppose we have k by eta equals lambda. Thus we can get equation 11 as d square x by dx square equals lambda x. This is an ordinary differential equation, so we assume the form of the function capital X equals a e to the power mx. This is the assumed form of the solution. Now, capital X equals a e to the power mx means that the solution x, which is depending upon the space coordinate x, behaves as an amplitude a multiplied by an exponential function e. Now, the exponential function has an exponent mx. Here m is the coefficient of x, which decides the rate of increase or decrease of the value of the function x with space. If we substitute this x equals to a e to the power mx into equation 11, we will get m square equals to lambda. This is because we have the double derivative of a e to the power mx equals a m square e to the power mx. So we have m equals to plus or minus square root of lambda. Now remember, lambda is capital K by eta. So depending upon the sign of K and eta, we can get different solutions. Nevertheless, we have x equals to a e to the power plus root over lambda x and b e to the power minus root over of lambda x as the superposition of two solutions. This is the general solution. Here a and b are constant coefficients. So we have x equals a e to the power plus or minus root over of k by eta. These are the two components of the general solution in space. We can have a look at a special case. For example, if lambda equals to 0, then this equation reduces to d square x by dx square equals 0, for which we have a linear straight line solution. This is a straight line solution where x is equal to ax plus b. This indicates the limit where eta tends to infinity. Now, we will consider the solutions and the characteristics of these solutions as we have derived in previous slides. First, we look into the spatial modes. Next, we will consider the various characteristics of the solutions, that is diffusion in one dimension. The first solution is x equals e to the power plus root over of k by eta x. Now this is a solution where the function rises with x. You can see the two solutions given in green and blue colors. The blue color rises much faster than the green color. The blue color denotes root over k by eta equals 5, whereas the green color indicates root over k by eta equals 1. Similarly, we have the next solution, capital X as a function of x equals e to the power minus root over of k by eta x. Due to the minus sign, this is a decaying solution. The green color indicates root over k by eta equals to 1, while the blue color denotes root over of k by eta equals 5. We can see that the rate of decay or the diffusion is controlled by the coefficients root over k by eta. Higher the coefficient, higher is the diffusion. Next, we have the time dependency. The time dependency also gives a decaying or rising solution. E to the power plus kt gives a rising solution, whereas e to the power minus kt gives a decaying solution. Note that as time progresses, we have a change in the magnitude of the solutions. For extension, we will look into the diffusion of various quantity in two dimensions. Here we have just shown a schematic solution of the two-dimensional magnetic diffusion equation as obtained from numerical solutions. The first at t equal to 0, if we have a concentrated spot in x and z directions, then this concentrated spot diffuses due to the gradient, and with progress in time, let's say t equals to 10, we have a diffused spot. Then as time progresses, the concentration of the initial spot diffuses and becomes more and more uniform. This is diffusion in two dimensions. Next, we look into the various applications in geophysics. The diffusion equation is used in geomagnetic field, as we have seen for the magnetic field application, and thus it was very important to understand the evolution of the magnetic field with diffusion process. The decay and growth of magnetic fields over time in highly conducting materials such as liquid iron in the Earth's outer core is governed by the diffusion equation. The diffusion equation also provides insights into the time scales for the magnetic field decay. For example, if the magnetic field is not generated by induction and we only have the diffusion, then any strong magnetic field which is existing will decay, just like we have the decaying solution in the previous slide. This indicates the reduction in magnitude of T with time. Thus, the magnetic fields decay over time if induction is not coming into play or the velocity is small. Next, we have magnetotelluric surveys. Magnetotelluric surveys is used to identify subsurface features using magnetic field and electric field measurements. In this surveys also, the time-varying magnetic fields diffuse. They diffuse through the Earth's crust and mantle. Thus, These signals can only exist up to a certain depth, and depending upon the frequency of the time variation of these magnetic fields, the diffusion acts. If the frequency is high of the magnetic fields, then they dissipate or diffuse out quicker. Hence, the depth of penetration in these surveys is limited. For deeper surveys, slowly time varying magnetic fields, which exhibit very less diffusion, are used. In core mantle boundary dynamics, the diffusion equation is used to model the interaction of magnetic fields with heat transfer processes and mass transfer processes which occur across the core mantle boundary. This is the boundary between mantle and the core. So this is a sketch of the Earth's interior, and the boundary between the outer core and the mantle is called the core mantle boundary. Here, the magnetic fields which are getting generated in the outer core interact with the various heat and mass transfer processes which occur at the core mantle boundary. To study this, magnetic diffusion equation and mass diffusion and heat diffusion equations are also very important. We also have variations in the electrical conductivity or eta across the core mantle boundary. Now, depending upon the variations in eta, the diffusion process vary from place to place on the core mantle boundary, and it has a huge impact on the Earth's geomagnetic field. Thus, not only one-dimensional diffusion equation, but multiple dimensions such as two and three-dimensional diffusion equations are very important for studying these processes. And to solve higher dimensional diffusion equation, we need methods such as numerical methods for solving and getting the solution. Thus, the magnetic diffusion equation describes the magnetic fields and how they evolve over time in conducting media. Now, conducting media exhibit resistive effects, and these resistivity effects enhance the diffusion of the magnetic fields. Now, we also conclude that the magnetic diffusivity, that is eta equals 1 by sigma mu, depends on the material conductivity and magnetic permeability. So this is a material dominated effect. Various different materials will have a huge range for the value of the magnetic diffusivity. And this creates a whole different dynamics and time evolution of the diffusion process. Thus, we can summarize that the magnetic diffusion equation is a vital tool for understanding the behavior and evolution of magnetic fields in geophysical and planetary contexts. It bridges the gap between theoretical and practical applications in geophysical exploration studies and also fundamental geoscientific research. One can have a look at these references for more details of the magnetic diffusion equation and the solution strategies and their applications in various domains of geophysical and geomagnetic studies. Thank you.